This is Tiananmen Square in Beijing. On its southeast side, there is Temple of Heaven Park with the size of 4 times of the Forbidden City. The Hall of Prayer for Good Harvests in the Temple of Heaven is an outstanding representative of ancient Chinese architecture. 3 years ago, I was fortunate to visit this world cultural heritage. It was indeed very magnificent, and the on-site experience was very breathtaking. It is said that the ancient Chinese built buildings by making scaled-down wooden models. In the 21st century, with 3D modeling software, I plan to try to remake it on the computer, build a digital model, and explore the proportions and mathematical relationships of the original design. As for why there is no material on the roof, I will tell you through this example that there are 2 ways to transform the geometry created by Dynamo into revit. One is to control the position of columns, doors, and windows through the positioning points in Dynamo, and the other is to import directly. In this case, there is no information and material, only an import symbols. This behavior is different from Rhinoceros 3D. As a parametric design enthusiast, I certainly don't complete the entire modeling manually, but let the Dynamo script help me do it, and what I have to do is to write a script. In this script, I can adjust various parameters to control the final building shape. For example, adjust the radius of the first floor. After modifying the number representing the diameter, and then click Run to see the modified result. No matter whether the number is changed to a larger or smaller, it can be used as a parameter for back and forth adjustment. This is the process of design. We can also adjust the wall height of the first floor. After the modification, because other height parameters are linked in the script, they will be modified accordingly. Then I'll show the adjustment of the radius of the roof. It can be adjusted accurately by numbers instead of scaling, so that the geometric shape of the building can be accurately controlled. Finally, I'll show the number of rafters of the roof component. Because the basic formula is done, there will be no situation where the number of rafters is insufficient or exceeded. Through the background preview, we can initially hide the nodes in Dynamo and view the appearance of the entire geometric shape. In this script, in order to add a list grouping node which the out-of-the-box nodes do not have, I used ChatGPT to help me write a Python code. Dynamo has always been able to add Python custom nodes. Here is the original chat history. If you are more proficient, you can also write it yourself. I have learned the basic Python syntax and keyword usage methods, but since there is an AI tool ChatGPT, I'll let it help me write it. Now let's see the 2 ways of interacting with Dynamo geometry to revit. First of all, the columns. The 4 innermost columns are called diamond gold columns. The positioning is controlled by the circle created in Dynamo. The method I use is the inscribed polygon in the circle. This polygon includes a rectangle with 4 sides. The corner points of the polygon are used as the positioning points of the column. At the same time, the properties of the columns such as the bottom and top heights are set. Now click Run to create the column. For the gold column in the middle circle, it is an inscribed regular dodecagon. 12 also symbolizes the meaning of 12 seasons. I will talk about it later. Click Run and the column will be created. Finally, there are 12 eaves columns in the outer circle, symbolizing the 12 hours in ancient China. 1 Old Chinese hour is equal to 2 hours in modern times. The same method can create 12 columns with 1 click, instead of manually finding the position and placing them by rotation or array. Next, I will show the component called Fong, which is similar to the current beam. In fact, I also use the method of creating beams to place these components. In Revit, you can manually create liner beams and arc beams, but you can't create a whole circular beam. This is different from the wall. The wall can use a whole circle, which I have demonstrated in my previous video. So you need to split the corresponding circle to get a segment of arc. There are many ways to split. I use the point on the curve to split. Now unfreeze the node to create the beam, click Run, wait a moment, and 2 circles of components called Fong are created. Here, I copy them and translate it in the direction of the z-axis according to the actual situation. There are 12 fangs in each circle, and 24 in total for 2 circles. As for the second floor beams, it is the same. Unfreeze the creation nodes, including the nodes for copying and translating, and set the parameter values such as the type and height of the beams. Click Run to create them. Finally, the third floor beams are created. The methods are the same. The beams of different heights have different sizes, considering the performance of the material under load. For the convenience of demonstration, I have isolated them in a view here. We can unhide the column category and see the relationship between them. The beams and columns are connected to form a frame, which is conducive to improving the stability of the building. Next is the roof. This time I directly use the method of importing the geometric shapes created by Dynamo into Revit. I have made a list here, which includes the roof panel and the upper and lower side components, and then use this built-in node to import. Right-click to unfreeze, and then click Run. You can see that the Dynamo geometries are imported, but this method is not recommended, because the imported components do not belong to any Revit family categories, nor do they have informations and materials. They are just simple importances. I won't show the roofs of the second and third floors. The process is the same. I will add the decorative components on the top of the roof. According to the online inform, 200 tails of gold were used to make this top component. I didn't build it in Dynamo, but solved it by placing a generic model family. So what I need is the center point of the top circle center as the positioning point for placement. Click Run to place it. It would be very troublesome to build such a complex component through Dynamo. It is much more convenient to solve it with a family. This view also comes from someone who has trained Grasshopper. He used Grasshopper before and wanted to create all graphics with it, but some of them were very troublesome. It was very fast and simple to do it directly in Rhinoceros 3D. As for walls, doors, I won't explain much. There are a lot of cases in my previous videos. One thing to note is that the circle of Dynamo cannot directly generate a circular wall. This is different from what is picked up by CD, so it will be better to divide it into several arcs manually. Finally, there is the dugong, which is essentially a regular model family. It is placed along the lower edge of the roof in a circle, so you only need to divide the circle by number. The regular points obtained are the positioning points for placing the dugong. Click Run to place all the dugong, because the distribution of the points is uniform, and the dugong are naturally placed at equal distances. The only thing you need to pay attention to about the dugong is to control the direction of rotation of the family, because the default placement is facing one direction, but in fact it is not. Each dugong T starts from the center of the building and is in a radiating shape, so you need to add a few nodes to control the rotation direction of the family. The last part of the model is to place the plaque, which is the same as the previous top component. Control the three-dimensional coordinates of the space and control the angle. After the model is built, let's explore the proportional relationship of this building. I declare in advance that I don't have the complete drawings and related data of the Hall of Prayer for Good Harvests, so the data are all pieced together, and because the ancient units are not integers after conversion to modern ones, it is just an approximation, not a very accurate model. First is the width-to-height ratio of the entire building. Regardless of whether the width of half of the outermost column of a certain surface of the first floor is calculated or ignored, the width-to-height ratio is close to 0.7, which is the silver ratio. The silver ratio is 1 to the square root of 2. In modern architectural design, Japanese architecture uses this more often. Then there is the ratio of the peaked roof. The diameter of the bottom roof is 27,000, and the diameter of the top roof is 18,900. Moreover, their heights relative to the second floor peaked roof are 5,200 and 7,200 respectively. After observation, the diameter of the top roof compared to the bottom roof is also found to be close to the silver ratio. Next, let's analyze the height of the building. I checked the data and found that the height of the Hall of Prayer for Good Harvests is 31.8 meters. According to the ancient size, it is 9 zhang, 9 qi, 9 cun, and fen. However, I checked again and found that the lengths of zhang, qi, cun, and fen were different in different dynasties. I took a relatively close value, that is, in the Ming and Qing dynasties, 31.1 centimeters was 1 qi for carpenters. After calculation, it was found that 9 zhang, 9 qi, 9 ciyuan, and 9 fen were close to the building height of 31.8 meters. Then there are the meanings of several columns. First, there are 4 diamond gold columns on the inside. Regardless of their number or the 4 directions they face after connecting, according to the information I checked, they represent 4 seasons. As for the 12 gold columns in the middle circle, they represent 12 months. And the 12 eaves columns in the outer circle, as mentioned before, represent 12 hours, and 1 ancient Chinese hour is equal to 2 hours in modern times. Finally, let me introduce the soul of Chinese ancient buildings, the dugong. This time, I also supplemented my knowledge of the dugong. This is the 3 view of the dugong, which is the top view, the front view, and the side view. Then on the left is a 3-dimensional drawing of the components of the dugong. The bottom of the dugong is called the sitting dough. In fact, it is similar to the shape of the dough which I'll introduce later, but slightly larger. It bears the weight of the roof supported by the entire dugong, and transmits it to other components of the building. Then looking counterclockwise, it is a component called the gong. The dough and gong are the core of the dugong component, and the gong is the main force-transmitting component. Next is the qiao, which is smaller than the gong, and it is also an important component for the various components of the dugong. Then there are the xing and dou, which are parts that connect various components. The difference between dou and xing can be understood as the difference between a cross screwdriver and a flat screwdriver. The groove is the way the mortise and tenon of ancient buildings are fixed and connected. Finally, this is a component called ong, which is relatively obvious from the appearance. It is mainly for decoration and also has a certain force-bearing function. In addition, I searched for information online and briefly summarized the evolution history of the dugong. First of all, the ancient Chinese used wood to build houses, and they also placed wooden beams on the columns. However, unlike modern concrete and steel structures, it is not easy for wood column and wood beam to connect. The beams on the columns are easy to slide left and right, which is not conducive to the stability of the building and very unsafe for people living in it. Therefore, the ancient Chinese first thought of using nails to connect, but nails have certain damage to wood, and metal is not as easy to obtain as wood in ancient times. Then they thought of digging a groove on the column and then placing the wooden beam, so that the sliding in one direction can be controlled. The connection between wooden beams also uses this mortise and tenon structure. According to the terminology of building structure, it is called adding constraints in one direction. Because they are all main beams, the load needs to be transferred directly to the columns instead of passing through another beam. So the wisdom of the ancients opened more grooves and adopted this mortise and tenon connection method. This picture is a picture of the disassembly of the column and the beam openings in different directions. This is the reassembled picture. The freedom of the column increases the constraints in 2 directions, making it impossible to slide at will. However, after the groove is opened, whether it is the end of the column or the position of the beam opening, the material's stress performance is affected by the opening, so the ancient Chinese came up with the idea of using the material wasted by the opening to add it to the part where the beam and column are connected to deal with tension, pressure, and shear. This is a picture of the disassembly after local reinforcement. And the end reinforcement part, which later has a name called dugong, has evolved through dynasties. It has become beautiful while hold the load of the roof, and it has become what we see nowadays. For example, this dugong disassembly picture, in fact, my dugong 3D view is based on this picture. Back to the whole model, a circle of dugongs transfers the load of the roof, while avoiding the possibility of excessive size and increased weight. Instead, it has become a major feature of Chinese ancient buildings and a symbol of pavilions and ancient buildings in various scenic spots. The above is all my video content about the 3D model of the Hall of Prayer for Good Harvests. Thank you for watching.